All right, sorry about that, guys. So thank you all for joining and waiting patiently. We have a really awesome session for you guys to see here today. My name is Martin Searle with AWS Professional Services. So we work with large enterprises on their migration to the cloud. We started working with Toyota Racing Development beginning of this year on their architecture for real-time data ingestion. And what they ended up running with and building is one of the coolest things I think I've ever seen. So we knew that we had to get them up here to talk about the awesome stuff they're doing. So without further ado, I'll give you Jason Chambers and Philip Lowe with Toyota Racing Development.
Hello, thank you. This is how Toyota Racing Development makes racing decisions in real time with AWS. In this session today, we're going to talk about how we use DynamoDB and many of the challenges that it brings to our particular data set, specifically time series data. We use this with DynamoDB and we stream it out using DynamoDB Streams. We'll be talking about that. And also how we take these DynamoDB streams and use the data real time, and also how we have what we call a turbo mode, which is going to be an accelerated way to reread these streams, something you can't do natively with DynamoDB Streams. We are Toyota Racing Development. We handle all of the technical aspects of Toyota's motorsports program in the United States. We develop and fabricate engines for all of Toyota's motorsports programs in Costa Mesa, California. And we also provide data and software solutions to our team partners. For the major series NASCAR, that would be, we have 5 drivers in that series: number 11, Denny Hamlin; number 18, Kyle Busch; number 19, Carl Edwards; number 20, Matt Kenseth; and number 78, Martin Truex Jr. So at Toyota Racing, we use data in almost everything we do. It's, on a day-to-day basis, it's all about data and analyzing data. And we can kind of take our data and divide it into two types of data. One is more batching. This happens pre-race. This is stuff that happens during the week leading up to a race. Our race engineers will take and model simulations that they can do to modify cars. Even though it's stock racing for NASCAR, there's still a number of things that we can change, modify, and swap parts in and out. And our race engineers use our systems to make better predictions and make better decisions on how to modify the cars and prepare them for the coming week. They do this so we can have the fastest car every weekend. We also work with the drivers. So we'll take data that we have in between practice and qualifying sessions and give them visualizations they can use to help improve their lap times. We want every time to qualify in the top and be starting every Sunday in the top of the field. And again, this is data that we batch. This is something that doesn't need to be real time. We have time to batch it, process it, and get it ready, but we do need it within minutes. And this is opposed to live data, what we'll be talking about today. This happens during the race. This is real-time data we're feeding through. We're making real-time analytics on this, analyzing this, running it through simulations, and we use this for split-second decisions during the race. Our crew chiefs use the visualizations and data that we provide them in order to make real-time race strategy decisions. So they use that, and they need this data right away. In NASCAR, things happen very quickly. Some of our tracks are only a quarter mile long, and they have, our lap times are 25 seconds. They have to make a decision. If there's a caution, they need to decide right away whether or not they're going to pit. If they pit, how many tires they're going to do, and what other modifications are going to go into the car. And we need this data within seconds. We don't have time to wait around for it. In fact, one of the favorite things I like working about Toyota Racing Development is every week I get to see the results of my work unfold every week unfold live on Sunday. Here's Philip.
So, I'm now going to talk about how our services are set up at TRD to provide this real-time data to the track. Most of our real-time services and software are developed on JavaScript here at TRD. In relation to the application we're going to deep dive into called Athena, we've built the backend on Node.js. The dynamic data which we receive live during the race session, so that includes practice, qualifying, and the race, we store that into DynamoDB Streams and also Mongo. And for the persistent data, so the storage of that dynamic data for long-term use, we also use DynamoDB, but in addition, we keep a copy of that in S3. And finally, for the caching services, we use Amazon Elasticache. For the front end, also done in JavaScript. We've based the framework on Google Polymer. And the dynamic data which the backend is processing is served up to the clients via a Meteor stream. So I'm going to talk about how the data flows through our components in the Athena application. And we'll start from the left, and we'll work our way to the right. So the starting point is the raw data feed we get from NASCAR, which is the live timing feed. So that comes in, it arrives into our first component called the data scraper. In this sense, it's the NASCAR track data scraper. And the function of that component is simple. It passes the raw data feed into a JSON object and stores into DynamoDB. We also have other data scrapers, such as the weather data scraper. And as you can guess, that scrapes live weather from the track and also stores that into DynamoDB. In addition to storing it into Dynamo, we have a Lambda that's running, which takes a copy of that and keeps pushing that into S3 via Firehose service. So once all the data is in DynamoDB, the first component which actually works with this raw data and starts adding value to it is the arbiter component. And what that does, it takes the raw data, interleaves it by time, and then starts adding additional metrics to it, such as gap to the current front or gap to the leader. And doing all those calculations, we need to be able to maintain state should there be any outages. So we are constantly caching it periodically to Elasticache should there be any problems. In addition, we also take note of the sequence number which we're reading off the DynamoDB stream, and we checkpoint that with our state, and we also cache that together. So if there is something bad that happens, we can resume our calculations and also resume exactly where in the stream we last left off when the crash happened. Once the arbiter is done processing all the calculations, it stores it into 3 separate locations. Firstly, a subset of the calculations are stored into MongoDB, where that gets streamed up to the end clients via Meteor stream. And second and thirdly, we store it back into DynamoDB and to S3 again. And that purpose serves is to support the race engineers to do their pre-race and post-race analysis on this data.
All right, let's talk DynamoDB. This is the first point where data comes in. And there's a number of reasons we chose DynamoDB. Of course, we want the decoupling of the collection of data to our analysis. We never want an issue in analyzing the data to ever cause an interruption in our ability to collect raw data. And DynamoDB provides an easy abstraction where people can write and we can read it out. We can have multiple data sources coming into DynamoDB, and it's very easy to scale up. As we are adding more data sources, we can increase our write throughput to handle additional data sources. And we can listen to this as a stream. This is very important. Live during the race, we can stream the data out. DynamoDB has what's called DynamoDB Streams, and this is essentially an oplog of DynamoDB. Every create, update, or delete gets streamed out through DynamoDB Streams. And then, as a byproduct, because we're using DynamoDB, this data is stored permanently. We can go back, our race engineers can go back to previous races. As we return to the track, they can look at previous years we've been there, and they can run more macro level analysis on this data. And it'll persist as long as we want it, which is forever. And of course, it's an AWS managed service. Unlike some of the other databases that AWS offers, DynamoDB is completely managed. And in fact, really the only 2 settings you have are how much write throughput you want and how much read throughput you want. And we also have the added benefit that using IAM roles, we can easily do access control. And it's not just on a table level basis. With DynamoDB, we can control who can see what columns, and we can even use access control to determine which rows are shown. Let's go even deeper into DynamoDB and how it works, because we want to talk about hot hashes eventually. So I like to describe DynamoDB as a map of binary trees. And when you use DynamoDB, when you create your primary keys, you divide your primary keys into a hash and a range. Your hash is going to determine what partition your data is stored on, and eventually which node within DynamoDB that is. Which means records with equal hashes will end up on the same partition and also in the same node. But this also means that if we want to query data and get a specific record, we have to at a minimum know the hash. If we don't know the hash, it's going to end up doing a table scan, which are very bad in DynamoDB. Once we get to the partition and the node where it's stored, we can use the range. The range part of the primary key determines how the data is sorted within that partition, which means that we have a combination of both the hash and the range, then we can go immediately to the record that we're looking for. And these are very fast queries. But it also means that when we first start developing our DynamoDB solution, the selection of the hash and the range has probably the largest performance impact of your DynamoDB solution. And it can make or break whether your queries happen on time and if it's able to scale up. And on the Amazon website, through the developer guide, they have a number of suggestions and maybe ideas for how you might choose a hash. And we have one here for time series data, item creation date. We can round to the nearest day, hour, minute. It doesn't matter. Amazon says it's bad. It is because all of our data is going to end up in the same partition. It'll end up in the same node. And by the nature of our race, we're always going to be very much interested in what's happening now. Our race engineers are always going to be interested in what happened last week, whereas races that were in the past, little less access to those. But remember, in order to access data, at a minimum, we have to know the hash. So this means our desire to eliminate hot hashes is in direct conflict with our desire to access data for a particular query, for a particular race. So we need to eliminate the hot hashes, but still be able to query our data in a time series way. So there's a few ways we can mitigate this. We can use separate tables, we can use manual hashing, or we can use composite keys. Separate tables is pretty simple. We just create a different table for every race or every day, and it all lives together. But we can do some things such as older races where we're not accessing them very often. We can tone down the read throughput and the write throughput. Whereas the most recent races, everyone's going to be interested in, we can tone that up. Next is manual partitioning. This is something where we have time series data. We have a lot of data that's coming in this case, November 20th. But we don't know we want to make sure it's not all going into the same node. We can just manually take a random number and add it to it. In this case, I took a random number from 1 to 10. This is good. This gives us a real good random, even distribution because we're using a random number on here. We're not limited to 10. Depending on how much we need to scale, we can go up to 100 or 1,000. The important thing to note, though, is when it's time to query this data, we're going to have to increase the number of queries we do. If we want an entire race worth of data, we have to now do 10 queries. And this isn't as problematic as it might first seem. Because of the nature of DynamoDB, data is already partitioned out amongst multiple nodes. So in fact, our ability to query this in 10 different parallel queries actually can increase our throughput to getting this data. The next solution is composite keys, and this is what we used at TRD. It's essentially the same thing as manual partitions, except instead of using a random value, we're going to use a known value that pertains to that record. One example we first started with is the record type. The record type, for us, tells us where the record came from, the source of the data, and what type of data it has. So if we have roughly 20 record types, this could cause the same distribution as, say, a random number. But it has the added benefit is if we're looking for a particular piece of data or a particular source of data, we can narrow in on that right away and not get extraneous data we're not interested in. When we first started doing our proof of concept, we started with the easiest, what we thought was just the race ID or the date. And this works great for 1 or 2 races, but as we add more and more data, we start seeing that it's taking several minutes to come back, which is not a great experience for our race engineers. As we added the record type, that helped us out a little bit. We got our queries down to about a minute, still not good enough, which then leads us to our final iteration, which was also adding lap number. So if we have a race with 500 laps and roughly 20 record types, we're going to be able to partition our data up into 10,000 different partitions and potentially up to 10,000 different nodes within DynamoDB for parallel queries. And it's important to note that even if it's not called a date, if it behaves like a date, we're going to have the same problem with hot hashes. If we call it race ID, it's behaving just like a date, and we're still going to have the same issue. So with this solution, we can now query the data all at once, and we can get the data as fast as we need, and basically as fast as we can analyze it, we can stream it out of DynamoDB.
And it's gone. So I'm not going to talk about the real-time aspect of DynamoDB Streams. Let's hope that stays. So as you recall in my earlier slide, the Arbiter component was created to monitor DynamoDB as streams. And it does this by issuing a set of AWS API calls to essentially tail the stream for updates. However, here at TRD, we've written a JavaScript wrapper which simplifies all these calls and makes the invocation a lot easier. And we share this across all the other TRD components and services which need to do this as well. Now, it's important to note that if you're a native Java developer, that AWS already offers this library on their website. It's the Kinesis client library. You can download it now, available out of the box, and it does the same thing. However, we do feel it's important to understand what's going on underneath the hood so you can sort of appreciate what KCL is doing to handle the complexities of managing or tailing a DynamoDB stream. So let's run through the basic calls that you need to do to actually tail the stream. So you first start off by issuing the listStream API call. And what that does, it returns you all the stream arms which are associated with your AWS account. So these are the blue arrows here. So we're interested in the biggest blue arrow for this example. So we'll find that based on the description, and we'll take that stream arm, which is a GUID unique identifier, and we'll feed that to the next call, describe stream. What the describe stream call does, it will return to you all the shards associated with that stream. So depending on how long you've been running it, you may have multiple shards. And what we're after is the active shard, the shard that's currently receiving data. Once we've identified it, so in this case it's the box right at the bottom here, we'll take that shard ID and we'll feed it into the next call, getShardIterator. And the function of getShardIterator is to give you a pointer on where the batch of records you want to pull out. And I'm going to elaborate on this a little bit more because at TRD, the options given for the getShardIterator has made it very easy for us to move around the stream based on different race scenarios. So the getShardIterator has 3 to 4 options you can feed into it. First and secondly, it's the after or at sequence number. And as you recall, we can do that to pinpoint exactly where in the stream we want to resume from, which is perfect for crash recovery. So every time we read a record, you get a sequence number. You can store that, cache that away, and you can resume to it whenever you want. Thirdly, there's the trim horizon. And the trim horizon allows you to move right to the beginning of the stream. So if we were to start up our services late, we can move straight to the beginning of the race without faffing around looking for a sequence number or looking for time dates and all that. We just hit trim horizon, off we go. Now, it's important to note that you can only go back as far as 24 hours. That's the maximum retention period for a DynamoDB stream. And finally, you have the latest, and that moves you to the tail of the stream. So that's our default operation mode. Whenever we start it up, we go straight to the tail of the stream, and off we go. So that'll be race start. Now, as tables have partitions, as Jason was talking about, streams have shards. And shards are bounded by a min-max hash ID and a min-max sequence number, so shown by the box at the top in the diagram. Now, if you think about it logically, as you fill up the shard, finally it will get full, and a new shard will be created. And DynamoDB does this automatically, so you'll get expired shards and you get new active shards. Now, DynamoDB will also automatically shard for you if you had increased throughput requirements, specifically increased write throughput requirements. And it does this by splitting your shard, which is great. It's very useful. You can scale your input automatically. You don't have to do anything. It just does it for you. However, it does pose as a double-edged sword because as you recall from the previous slide, you need to track the shard iterators to get your records. So you're no longer tracking one shard iterator, you're tracking 2. Or if it's sharded up for you again automatically, or 8 or more. So then tracking could become problematic. So this is one of the key problems we hit during our early development cycles, where when streaming, we had to actively monitor the shard to determine when it expired, because you don't get any notifications on when it expires. And when it does, you start looking for the new active shard. Now, the gotcha for us was we always expected the new shard to be available straight out. Once as soon as it's expired, when's the next one, we'll grab it and off we go. But that's not the case. There is a time lag from the point that it expires to the point a new shard gets created. So in order to overcome that, you have to continuously be looking for new active shards, also to handle when a shard splits in two. So you can imagine in our early development cycles, during a race, out of the blue, the system would just stop. And that's because we didn't handle the sharding correctly, and we didn't pick up the new active shard. Or in an other case, we only had half the cars updating because the shard had split, and we only caught one of the active shards. So how do we mitigate this? Commonly, we'll do functional tests to mitigate this, but it's difficult to do with DynamoDB Streams because you cannot control when a stream reshards. However, those who have motive kinesis may realize that the API is very similar, if not the same as kinesis. And you can leverage this. You can use kinesis to simulate the streams and force the resharding so you can test the handling of your code. In Node.js here, we use Kinslite for our functional testing. And if you are on the same boat, I highly recommend it. It's a very nice, light package which you can do to simulate this and trigger reshards. And just to reiterate, our most devastating bugs were due to the inability to handle the sharding within a DynamoDB stream. Since I've talked about kinesis, I thought it'd be good to provide a quick table just to show you the differences between the two. So let's talk about persistence first. DynamoDB allows you to persist data in two forms. First, as a stream, which allows you to store data up to 24 hours. And secondly, as a table, and you can store that for as long as you need to. For kinesis, on the other hand, it's stream only, so you can do that from 24 hours or up to 7 days. That's configurable in the console. Sharding, as I was talking about, for DynamoDB, it's automatic, which is good and bad. And for kinesis, it's manual. So if you know your load up front, you can set it and off you go. For querying, you can query DynamoDB either as a stream, which is series data, or as a table, ad hoc. Kinesis, as it's just a stream, that's all you got. You can only query it as series data. Stream latency. So we did tests at TRD as a full round trip writing out, reading back in. DynamoDB, we saw about 1 second latency, but for kinesis, we saw it drop to about 200 to 400 milliseconds. So there's some gains there. And finally, from a billing perspective, DynamoDB, they charge you on a per read basis, and kinesis, it's a per shard and write basis. So depending on use case, one may favor the other.
Cool. All right, let's talk turbo mode. We're going to bring in Firehose and Lambda. So we have a scenario. We're running, the race is going great. We're analyzing data. We're making our visualizations for our race engineers. And now our race engineers have discovered that the model is either incorrect or they found a better model that we want to switch to. And the problem is we want to reprocess all of the data as fast as we can and then catch back up live. Because DynamoDB Streams has a read limit. You can only read so fast. If we were to read it through the DynamoDB stream, the race would be over by the time we reprocessed everything. So our solution is to read the data from an alternative source and then switch back to the stream right where we left off. But the problem is we need to know exactly where in the stream we want to pick back up from. So our solution is when we're storing the data out to an alternative source, we want to store both the raw record and the sequence number for that record for where it exists in the stream. And Lambda provides a good way for us to do this. So nice, easy scenario. All we really want is we want our raw record and our sequence number. So we have our data coming in through DynamoDB. We've set up our streams. And then the top right box is our Lambda. And all we need is every time a new record gets created is to output it to Firehose, which will then output it to S3. And remember, when we write it to Firehose, we want both the record and the sequence number. This is important. And if you haven't used Firehose before, it's a simple AWS product. It gives you an endpoint. You throw as much data as you want into it, and then it will aggregate it together and store it in an endpoint. In this case, we chose S3. And it handles all that for you. So you just feed it data, and it sends it to S3. So now it's time to run turbo mode. So step one, we can now look at the S3 copy of all of this data. We can read it as fast as we can, as fast as we can process it and analyze it. And as soon as we're done processing as much as we can that's on S3, we now know the exact point in time within the DynamoDB stream for where we want to pick up. So now based on this sequence number, we can go back to our stream, and we have neither a duplicate record nor have we missed any records because we can pick up at that exact moment. And the result is now we can process in turbo mode and then switch back live as soon as we've reprocessed with the new model. And in fact, it's so easy to set up, we can actually just do this from scratch in a few minutes. All right, so before we started here, we set up an empty table called reinvent, nothing in it, and we have a Firehose that we set up. And like I said, Firehose is simply, you give it a name and an endpoint. In this case, we gave it an S3 bucket for where we want the data to go. You can have a few settings as far as how often you write. The lowest you can go is 60 seconds. So now to connect these two together, all we have to do is create a Lambda. And AWS creates a blueprint for you so you can process any kind of data coming out of DynamoDB. But before we do that, we need to turn on the stream for our table. So if we go to our table, turning this on from the console is very easy. We have a Manage Stream button here. And to turn it on, all we have to do is determine which kind of data we want to go to the stream. And we can choose, again, it's just an op log of every create, update, and delete. And we can have just the keys that were affected, the new image, the old image, or both if we want. So we turn that on, and that's turning on DynamoDB Streams. So now that we have that set up, we can come back to our Lambda dashboard and create a DynamoDB process stream. And you just tell it where you want it to come from, in this case, our reinvent table. And you can do the whole last 24 hours if you want when you're creating the Lambda, or we can just start at the end, which we'll do. And then you can batch them if you want. And we'll turn that on. So you give it a name, and by default, it just prints the contents of the stream out to the console. We'll start with that just to see what it prints out. And you can give it a role. I already created one that gives it access to that Firehose that we saw earlier. So we actually did see that it did not quite hook up. We'll come back to that. It's still creating the stream that we did earlier. So now if we look at the code, we can actually test it. DynamoDB gives us an example event called DynamoDB Update that we can use for testing it. And we can see it just prints out to the console. What we're really interested here is this record.dynamodb. And we see it prints out the keys, the new item, and most importantly, the sequence number right along with it. So for our simple case, if we were to just simply process out this record.dynamodb and send it out to the Firehose, that will have everything we need, both the raw data and the sequence number that we can use for coming back to the stream to pick up. So AWS, by default, in the Lambdas, already has the AWS SDK. So we can use this to create a Firehose. And then inside here, we can just send this out to Firehose. And this is just 2 lines of code I'm going to copy over. So the Firehose SDK has a method called putRecord, and it only takes a delivery stream name and the raw data. Firehose is all text, all strings, and it just aggregates them together. So it's important that you also give it some sort of delimiter, because it won't. So you need to add, in this case, we're adding a carriage return. So we'll go ahead and add that in, assuming I copied and pasted correctly. So we can see now, the callback, I just printed both the error and the result up to the screen. So we're putting the record and then looking at the error and the result. No error. And the result from Firehose is a record ID. So these are now being sent out to Firehose. So we're all set. Now we just need to send data from DynamoDB. We did have an issue adding the trigger earlier, but because we use the blueprint, when we go to add the trigger, it's all set up for us, and should work this time. So now we're all hooked up. So now everything is set up end to end. Any data we add to DynamoDB is going to call our Lambda, and our Lambda will then feed that on through to Firehose. We really like Lambda for kind of gluing components together. It's really easy, and we're not limited, obviously, to Firehose. If we want to look for anomalies in the data and put an alert in Slack if there's a problem with the data, there's really no limit to what we can do as the data is coming through to look at it. And I actually have an example of what it looks like. I did this a little earlier. So this will be the raw file that comes in through S3. So S3 will be a series of files of these, each one covering 1 minute of data. And we can see it has the raw data and the sequence number, which is the important part, that we can use to going back to correlating that from our raw data back to the feed.
Okay, great. So what you're seeing on screen right now are 3 of the common applets the race engineers use on track to monitor the race status. This application is called Athena. Unfortunately, it's not AWS Athena. Thanks, Amazon, as Jason was alluding to. And briefly, the 3 applets which you see, the top right corner is the race positions applet, and that gives the engineers a visual indication of where all the cars are on track. The bottom right-hand corner is the graphs applet that gives them a historical view of the lap times which have taken place on a per lap basis for all the cars. And finally, in the top left-hand corner, the leaderboard. So for anyone who's done any racing, go-kart, you'll be familiar with this table format. Gives you a table view of all the cars on track by their positions and their lap times. So let's talk about each applet a bit more in detail, just to give you guys an insight on what we use the live data for. So the race positions applet gives indication to the engineers on where all the cars are on track relative to the leader. That's why the cars don't move around non-stop like a GPS coordinates, because if you have a 25-second lap and 40 cars going around that, it gets quite busy. You can't really watch it. So the leader is static, and everyone moves back and forth based on their relative time to the leader. The 3 rings you see, the outermost ring are cars which are on the leader lap. The middle ring are cars which are a lap behind, and the innermost ring are cars which are more than a lap behind. Now, what's useful for the engineers when looking at this is that as they hover their mouse over the car of interest, they can see 3 additional icons appear, those square ones. Let me get the pointer just so you can see. These square boxes appear for car 19. And that indicates where the car would come out if he had pit at that point in time. And the 3 options you have is based on what they do at the pit. So would they take no tires, just fuel only? Do they take 2 tires, or do they take 4 tires? So this is all very useful for them, because then they can start predicting what can they do to get the car in clear air if it's on a green lap. And it's important because as you pit, you don't want to come out in traffic. Ideally, you want to come in clear air, and then you can make pace afterwards and do an undercut if you need to. Next, the graphs applet. So the graphs applet, like I said earlier, gives a historical view of all the lap times that has happened. And that allows trend analysis. And one of the things they like to look at is how is the lap tire, the tire degradation taking effect? Because as you run more on track, your tires degrade, your lap time drops off. Or that's always counted by the fuel burn. So the more fuel you burn, the faster you go. So these lines allow them to do this sort of analysis, and it's very interesting to them to do it live during the race. And as you can see by my virtual mouse, it's going up and down. As you hover across the dots on the graph, you can see the lap times. And finally, the leaderboard on the top left-hand corner. That gives them a table format of where all the cars are on track based on position. It tells them their last lap time. Was it their personal best, which is indicated by a green highlight? Is it their overall best, which is indicated by a purple highlight? It tells them when their last fastest lap time was, the rank is how the lap times are performing to the field at that point in time. And also it gives them time gaps to the leader. And that's very useful for them because if you were 0.8 of a second behind the leader and you knew that you're lapping significantly faster, you can do basic math to work out that I could catch up with this car in 8 laps. So that plays into strategy. Should you be fuel saving? Should you be pushing? Should I pit? So all these things are happening live. And that's what we use the data for. And that's why it's very important that we don't have any dropouts and have that continuity all the time. So that concludes our presentation. Thank you very much for sticking around with us.